Okay, let's try this page again. Last time I didn't print correctly, so I had to start over. On this first example, our polynomial is a 4th degree polynomial with a positive leading coefficient. That means it's going to be parabolic in shape, but it's going to do crazy stuff in the middle. So you see that it's both facing up on the left, up on the right, and it's doing this kind of slant thing in the middle instead of like a parabola normally does. The next one is also an even function. Negative 2x to the 6th is our leading term. The coefficient is negative, which means it's opening downwards, but there's going to be some crazy stuff going on in the middle, as you can see here. Then we have two odd-degreed polynomials. The first one has a leading coefficient of a positive 3, so we know it's S-shaped. That's not why we know it's S-shaped. We know it's S-shaped because it has an odd leading power, which is a 5. The leading coefficient is positive, so we know that it makes that general S shape with crazy stuff in the middle. Alright, and then finally we have a leading term of negative 6x cubed. It is again S-shaped. However, the leading coefficient is negative, which means it flips over. So you can see how it goes up on the left and down on the right this time, and in the middle does some kind of crazy stuff. Given this function f, express the function as a polynomial in general form and determine the leading term, degree, and end behavior of the function. Hopefully at some point you can just look at this and know the answers to all of those questions, but right now let's see what it looks like if it was written in general form. Let's go ahead and multiply these two. Remember, when it's multiplication, it doesn't matter which order you do them as long as you multiply them all together. So we'll get x squared plus 4x minus 1x minus 4. So x squared plus 3x minus 4 once we combine our like terms. Now we're going to distribute that negative 3x squared. Hopefully I did all my math correctly. As you know, being my students, you already know I do make mistakes, so double check and let me know in class if I make a mistake. So this is our general form. This is one of the things that they asked us to do. And determine the leading term. Well, the leading term is going to be negative 3x to the 4th. The degree of the polynomial is going to be degree 4, and the end behavior, well, let's sketch a little graph. This is an even degree, so we immediately think parabolic. Since it has a negative leading coefficient, we know that it's flipped over and not this one. Okay, so if we're looking at this, as x gets smaller, y gets smaller, right? So as x goes to negative infinity, y, or f of x, goes to, x goes that way, y goes that way. So it also goes to negative infinity. For the other direction, as x is getting bigger, y is still getting smaller. So as x goes to positive infinity, y, or f of x, goes to, let's say it again, as x gets bigger, y goes down as well, so it gets smaller. So I believe we answered everything they asked for in that problem. We are also going to be looking at the local behavior of polynomials. Here we have a graph of a polynomial. We can see the x-intercepts are where the graph crosses the x-axis. The y-intercept is where it crosses the y-axis. And then we have something new called turning points. This is where your graph goes from increasing to decreasing, or from decreasing to increasing. And where it changes direction like that is called a turning point. Given the polynomial function f, it's written in factored form for our convenience. Isn't that nice? Determine the x and y intercepts. Okay, remember to find an x-intercept, you always let y equal 0. So you have 0 equals all this stuff. Now we need to set each factor equal to 0. And solve. So we're going to add 2 and subtract 1 and add 4. So you actually have 3 x-intercepts. You have 2, 0, negative 1, 0, and 4, 0. Now to find your y-intercept, you always let x equals 0. Well, in that case, we have f of 0, or y, is equal to 0 minus 2, 0 plus 1, and 0 minus 4. That's going to be negative 2 times 1 times negative 4. Negative 2 times 1 is negative 2. Negative 2 times negative 4 is positive 8. So our y-intercept is the point 0, 8. Determine the x and y intercepts of this function. Just like before, to find an x-intercept, you let y equal 0. So you have 0 equals x to the 4th minus 4x squared minus 45. By now you should be able to factor this. If not, it's okay. Go back and review your factoring, but hopefully by now you can actually factor this one. So this will factor into x squared times x squared is how we get our x to the 4th. Factors that multiply to negative 45 but add to negative 4 would be a negative 9 and a positive 5. Always double check to make sure. Set them equal to 0. So we have x squared minus 9 equals 0 and x squared plus 5 equals 0. Add 9 to both sides. So x squared is equal to 9. Now we can take the square root of both sides. Don't forget plus or minus. So we have x is equal to plus or minus the square root of 9, which is 3. This one we subtract 5. We take the square root of both sides. Don't forget plus or minus. So we have x is equal to plus or minus. Now this is the square root of negative 5. That's I square roots of 5. Now what are we looking for here? We're looking for x-intercepts. Can we graph an imaginary number as an x-intercept? I don't think so. So this one doesn't really help us that much. So here we have the point 3, 0 and negative 3, 0 as our x-intercepts. Finally, to get your y-intercept, you let x equal 0. So f of 0 is equal to 0 to the 4th minus 4 times 0 squared minus 45. Well, that's 0 minus 45, which is negative 45. So your y-intercept is the point 0, negative 45. I actually want to sketch this graph and let you see what it looks like. Let's see, we have x to the 4th minus 4x squared minus 45. When I graph this, it's not going to show up very well because our y-intercept is at negative 45, and I want you to see that. So I'm going to change my window. Wow, it's changed to all kinds of crazy stuff. X-min, the standard is -10 and max is 10 with a scale of 1. But let's just see how we can do this. Let's change this to -50 and leave the max at 20. I have no idea if this is going to work. I'm just going to try it. Well, you can kind of see what's going on there. You can see that we have x-intercepts at -3 and 3. You can't really tell that that's -45, but it's way down there. And you know that I made my window -50. So you can tell that it's just above the -50 mark. And what I want you to notice is right here at this I square roots of 5. Let me stop that just a second. Square root 5. I just wanted to see what that was working out to be. Alright, so whenever your graph does a little turn back to the x-axis, but then it goes back away really fast, it's kind of like saying, hey, we're going to have another x-intercept, but no, we're not. Anyway, that's just my way of remembering. That's why we have these imaginary x-intercepts, because it's like your graph is tricking you into thinking you're going to have another one, but you really don't. Pretty interesting, huh?